So we're coming to the part of how we can interpret uh, interpretations of quantum mechanics. So before we're going to talk of interpretation of comments, so I want to place a couple of comments. The comments are that we since there is not a consensus of what we constitute as quantum reality, because in classical once we had a classical mechanics, the notions of reality and the notions of determinism, which was associated with classical equations of motion, dynamical or motion, we were very much clear that in principle we could state of a system of particles or individual particles can evolve from a given point to another point in universe or in a given system. But as far as the Schrodinger equation, as far as the psi, as a wave state was concerned, the idea of state, its evolution, it's subject to various interpretations. And the idea of whether we can determine or we can be deterministic in the classical sense. So there are interpretations to whether that deterministic, the classical determinism, can be that imported into quantum determinism or not. Or even those, since the frame, the fundamental idea is different, even the notion of determinism may not be, cannot be placed in that classical sense. So how is quantum determinism as an idea vis-a-vis the evolution of state psi? So there can be various interpretations to it, and one is as an operational physicist who are not interested in the finding foundational questions, but still recent developments in quantum information theory and so they have necessitated we relook into the foundations of quantum mechanics, what we consider as observer, what's measurement, and what is the reality, which is the admixture or which is the play of measurement and observer, and what is quantum reality, from which we construe quantum reality, and which may be slightly different from or having some aspects overlapping with classical reality, and fundamentally they are having some divergent interpretations. So to begin with, for example, so if I'll take Weinberg, so he uses, so for Bohr, so there have been many players in quantum mechanics like Schrodinger, Bohr, Heisenberg, Born. So in the time of 20s and 30s, so there are, the history is all as much interesting as the ideas. So if in the ideas of Bohr, if I used Weinberg, so the essential interpretation of new quantum mechanics is the fundamental distinction between the measuring apparatus and objects under investigation. Objects under investigation. So we have a fundamental distinction. So we have a sort of bifurcation between observer and what's going to get observed. So we here observer can be identified also with sometimes with this measuring apparatus. So this is necessary in accounting for the functions measuring apparatus. We sometimes measure apparatus purely in classical terms, and in principle modeling away the quantum of action. So sometimes measuring apparatus is has some notions of classicality in it. So for Bohr, it's also called Copenhagen interpretation of quantum physics, Copenhagen interpretation. So a measurement, measurement changes. Measurement changes state of the system. In a way which cannot be determined by quantum mechanics. Determined in the exact sense, the way in the classical sense, we could not. The observer was very cold. The measuring apparatus as such did not have any effect on the what was going to get measured. Because in classical mechanics, when we go to things, what we measure things, for example, a photon, so or a light, so at some the scales in which quantum mechanical theory normally works. So the measured and measuring apparatus, which so it definitely significantly changes the system in an uncontrollable ways. So measurement changes state of the system in quantum mechanics. Changes in the system, in classical mechanics, you could change that you could account for those changes. Those changes were insignificant, so we could neglect them, or they did not have any effect in principle. So if we measure an observable represented by Hermitian operator A, so and initially the system is in the state, it's the superposition of states, normalized superposition of states C and A n. So n goes to 1 to whatever, it goes to 1 to n. It's the superposition of these normalized states C1, A1, C2, A2, C3, A2, Cn, An. So the state will collapse during the measurement process. The state will collapse during the measurement process. So if it will collapse, so the observer will have only one definite value, which is An, and probability of finding the will be equivalent to this Cn square by the Born rule. So this entails a definite change in how we understand the dynamical quantities, and it's also given by at the end by Born rule. So those superposition of states at the end, that gets equivalent to 1, sort of the system is conserved in that sense. So from this Born interpretation. So the question is, so how does measurement entail a change in how we dynamical interpretation of things. How does it say it? For example, if we assume that Schrodinger equation is, if we have a Schrodinger time dependent Schrodinger equation, and we assume that time dependent Schrodinger equation which describes the measurement process. So the end result will be at some, it will be a definite process, because the idea of the process of measurement entails a certain different eigenstate to what is that eigenvector, which is represented by psi. So, and which means it's not a number of possibilities or probabilities. So if a measurement process in a time-dependent Schrodinger equation entails a definite eigenvector to a different eigenstate to a different eigenvector, a particular value, so it will not be the way we have probabilities or possibilities. So what? So this is unsatisfactory. This is unsatisfactory. Why should it be unsatisfactory? Because if quantum mechanics applies to particles, it must apply to measurements also, measuring apparatus also, which might include the observer, which in our case might be a physicist who is observing a given system, or quantum physicist who is observing a given system. So if a quantum mechanics does not apply to everything, so we need to say if quantum mechanical understanding is not, it's not encompassing, so we need to signify what may be the boundaries of how the quantum mechanical way of understanding. Does it impose some boundaries? Within that thing we can understand how the system or a dynamical system evolves from state A to state B. So it's not, so when a measurement process gives us a definite value to what we have observed in eigenstate, so it precludes the rest of the universe in the scheme. So the point is, does it mean that quantum mechanics, while you are measuring something, it will have some boundary of validity? So this thing has maybe there is another school. Basically, you can place also the idea of this measurement and quantum reality in the background of previous debate of how physicists not only determinism but causality also. That the effect can be traced to the cause. So the causal relationship between effect and cause, which was very strict, somehow in classical mechanics you can it comes out to be clean, but in quantum mechanics because the state psi, wave function psi, so we will not talk of we don't talk of certitude, we talk of psi in terms of probability, broad interpretation, psi and psi square. So psi, when we talk of certainties, when we talk of probabilities and possibilities, so what constitutes a reality? So once we give a measurement or an apparatus or observer, yes, by the act of observing, it will choose one possibility among the many possibilities. So where does it leave our understanding of causality or causal order, which is associated with it? Causality and how can we place determinism as a philosophy? So to circumvent this idea, there have been physicists like Max Born, there have been physicists like David Bohm following Einstein. So it's well known that Einstein and the school, they wanted to somehow rescue. They wanted to, they had an attachment to the idea of causality and causal order in terms of that idea of pre-established harmony. So the notion of so this thing, so if this idea of was taken by Bohm, so that we want to rescue causality. So if we have this interpretation of this time dependent Schrodinger interpretation, where measurement gives a particular value which might exclude the other probabilities or other possibilities, which will in turn somehow put in danger or make causality suspect in this understanding. So Bohm and other physicists, what they came up with something called non-local theory, hidden variable theory. So here, there are hidden variables which we don't know, which will account for the how, which we have not discovered, or which will account for the theory not being causal, or theory not choosing a particular. So there being something amiss once we go from state A to state B, that we are only choosing one possibility among the many possibilities, the measuring apparatus. So this is one possibility. And there have been other physicists who will not talk about hidden variables. They will say that we can include some non-linear terms in the Schrodinger equation. Non-linear terms in the Schrodinger equation. In the equation, or random terms, non-linear or intrinsically random, non-linear or intrinsically random terms in the evolution of equation of the state vector, with no hidden variables. So if we just follow the book, so Weinberg he will limit ourselves to the interpretations of quantum mechanics that do not entail in the change of foundations. So we are going to take this point of view, that we are not going to entail some fundamental change in the foundations. As such, we are going to drop these theories of hidden values in our. So what we are going to concentrate on, not hidden variables or not time-dependent modifications to the Schrodinger equations. What we are going to do is we are going to take two broad classes of interpretations. So we may take state vectors. One is either we take state vector seriously. This is one possibility. As a complete description of physical system. So the attempt would be to understand. In this scheme, if we consider state vectors seriously as a complete distance, so attempt would be to understand. So from this, the various probabilities or possibilities that determine the deterministic evolution of state vector. So this is one thing. So we are taking state vector seriously as a complete description of physical system, and following that thing, we should be the deterministic probabilistic evolution, but which is deterministic evolution of the state vector. So this is one thing. Or the other thing is, or what we are going to do, we may give up objective description of physical states, and we only express the state vector or state vector as group of possibilities or probabilities. So we will not. So once we believe in that causal order, and as an observer having the objective, he could objectively see how the state A evolves from A to B in the classical sense, and we could place determinism that way also. So rather than taking things that way, we are going to give objective description. But what we are going to take, we are going to take state vector fundamentally as if they are group of possibilities or probabilities, and we have to see how those probabilities of that state vector evolve vis-a-vis time. So maybe one is that the observer, the measuring apparatus gives a different value to what is going to get measured as a different state in that deterministic sense. The other is that we don't talk of a definite state, we talk of probabilities or possibilities of a state branching into different states. The second one can be, for example, in homogeneous, if you have an Stern-Gerlach experiment, sometimes how a given state atoms are passed in homogeneous magnetic field, how different components or atoms in that, how the components add up and give the total state. In this particular, the way we talk of J, X, J, Y, J, Z, and other things in the thing. But according to open interpretation, and state vector Jx measurement will assign a different value to it. But if you have the other interpretation, so you can have you can add. We can add the different states, different probabilities and possibilities, and at the end add them together. And there is also a third possibility. Third possibility, which was, or in the words of Weinberg, a dramatic way, melodramatic way, or way of putting things by Schrodinger, which is famously called Schrodinger's cat. That if you have a container or if you have a box, in that box there is a cat which is already sitting there, and the external observer, but that's the closed room or closed apparatus in which that cat is there, but the observer outside is going to shine in radioactive light by which he will detect it. But inside that apparatus, we don't know whether cat is alive or not. For cat itself, it may be alive, or it may once it's inside. But once we use an imaging apparatus, it's going to, the measurement is going to just kill it. But for the observer outside, so he has two possibilities. He sees cat dead, this is one thing, or he sees, according to the second interpretation, cat dead as well as alive, a superposition of two. In one state, when he has not observed the cat, so it might be alive. The other state in which the observer and the observed cat is just interacting with that signal, and by which it annihilates it. So it's the linear combination of the dead and the alive cat as two possibilities of this thing. So it may sort of lead to conundrum or a paradox in that sense, but you can see that there are two interpretations of looking at these things. And this set of the second interpretation, it's also called in literature, it's also called mini world view, or Graham David. David was a physicist. David's no, sorry, David Everett. Everett. His PhD thesis. It's interesting. How we can interpret. So, in the process of observing the things, there are many possibilities that state vector can take. So, and the reality can branch into many realities. So, there can be two things. In the act of observing, in the act of observation, in this interpretation, it will preclude other possibilities. But in the second case, you have to take the state as a evolution in the many histories. In the second case, the history becomes important. So where from you start, there can be many ways or many worlds in which a state vector psi can evolve as components also. And net real thing is that these all components have to be taken together as a sum. But in the first case, Copenhagen case, the act of observing is going to choose one reality and preclude the other realities. So these are questions. Not only they deal with not only physics, they also have a metaphysical elements in these questions. That so whether we take universe, if we so far, even if we take many worlds, many realities. So from where did they many realities? Those realities start from a single reality and then they branch into many realities, or whether they will again come and dissolve into one reality. So these branching of reality into many realities, or branching of world into the many worlds before the act of observation. So these are also metaphysical questions apart from physical questions, physical answers. So as an operational part, what we're going to say is that now what we are going to say that. So the first step in the measurement is an evolution of state vector in Schrodinger picture, which establishes a correlation between system under study so it's so in the first case, we can have a collapse of the state vector to a definite value, collapse of the state vector. But in the many world view, world's interpretation, we can do things without invoking this collapse of state vector into a different value. Now, what we are going to do is see that, for example, so in the, if you want to have a meaningful this second interpretation, that state vector psi, it's going to just have components. The Schrodinger cat can be the two states, maybe one state which is the linear combination of the measuring apparatus and the cat, and the other is the in which it has not been the cat has not been dead. So you can have continuous possibilities of a linear combination of a state which is being measured under measurement and other states. So the question is how we are going to account for the total measurement of a given system, which includes measurement, observer, and the observer. And observer is the state of the system, and the state of the system, its evolution included. So, for example, what we are going to see, suppose a macroscopic system, suppose a microscopic system can be in a set of various states labeled by the index n, while the apparatus may be labeled with index a, so that the states of the combined system can be expressed as the combined orthonormal states, like the psi of NE. So there must be at least many apparatus states A as the system N, and many more. That's the point. So the apparatus is placed at time t is equal to 0, and the suitable initial state may be A is equal to 0 with the microscopic. So the general states of combined states may be this combined state system of the state vector can be Cn psi, but we have started, since we have started the state 0, it will be psi n 0. Fine. Now what we are going to do, we are going to turn interaction between the microscopic system and the measurement apparatus. So the measuring apparatus and the system, they are going to see how they are going to interact, and the system will evolve. System evolves in time t to u of psi of 0, where u is the unitary operator. U is exponential of u is the unitary operator acting on the state psi, which is at a, v is giving this thing. So we are free to choose Hamiltonian H for this unitary operator, for the unitary transform. So for an ideal measurement, what we need is that psi of 0 of any basis, psi of n0 then evolves into the state n of 0 should evolve in the state psi of 0 and a of n, where n is unchanged, and an is labeling some definite state of apparatus in E corresponds with the state of this psi that an is not equivalent to an prime, and n is not equivalent to n prime. So we are going to take a state, and either one is that you go from an state A to this 0, but you can have any state. It's not necessarily it will go from, it can go from 0 to any state, n state. Now the point is that If an is not equivalent to n prime, n is not equivalent to n prime, so we need to have so we can have a state going from sorry, n prime, a prime, n 0. These are the indices, so they will have n. The second one is a prime n. So these are two states. A state where definite n to a, this and this. Now, from our previous understanding how we can have those orthogonality functions and orthonormality conditions, so you can apply them here for these two delta functions. So you can have u of n if a prime, n prime, a prime, n of a is delta n prime u n a prime a. So a prime is not equivalent to a n, or a prime is equivalent to a n. So for this, so we can have different values, and this is equivalent to 0. Where the matrix, so you have some unitary operator which is acting on the state function psi, and for a certain state that correspondence is there, and certain orthonormal states. So for orthogonality condition, you can have this thing, or a naught this equivalent to this, it's 0. And if it's not for two states n going to n, this going to this thing. So the question is how we are going to represent delta a prime is equal to a prime a n u a n star u a prime. So it's basically you are representing two states by states, and there is a unitary operator which is acting on those two states and their evolution. In one of the states, it chooses a definite value. In the other state, the values may vary. So the point is that, so the matrix, so if you see this thing, the matrix, the matrix is u a prime a n or square, because a prime runs over all at state except at a n. A prime is equal to a n, and a runs over all apparatus except a is equal to 0. So it will run over all states except one is a will run go for n, or it will run for all except a will go for 0. The condition is simply thus: the condition that these submatrices are unitary. These submatrices are unitary. They are unitary, and they are not subject to constraints. So we can find any number of matrices. That's why the condition. So we can check the condition that this equation, this and this equation make the whole matrix unitary. This and this condition will make whole matrix unitary, such that after the measuring apparatus, after the microscopic system and the measuring apparatus have interacted and combined in the state vector u psi naught. So u psi. So according to this, thing, the superposition of the states is So it's basically how you can have before and after measurement after the measurement which is given by a unitary operator acting on a state psi, how it evolves under these conditions. In condition A, this is equal to this, and in condition A runs from all apparatus except that A is equal to 0. So maybe there is also a digression by von Neumann. Von Neumann has been a mathematician who has worked on this aspect of quantum mechanics. So a frequently quoted example of this Neumann is that instead of discrete indices n and a, we can characterize position coordinate as x, which is defined as the x as the pointer of the particle, and Hamiltonian being written as minus omega xp, omega being some constant, p is the momentum operator. So we can, the way we have position and momentum operator such that the commutator of the position and momentum is not necessarily 0. It's iota h. And if t is equal to 0, the coordinate space wave function being represented by they being represented by psi of x0. Psi of x0 is equal to f of x minus zeta g of x. So if f and g, so here we are going to use how to define those delta functions. So the value of a function which will remain maximum at its origin, and it might be 0 otherwise. So if we have two sharply defined functions, psi of f of 0 and psi of f(x) t, which is going to evolve in space via these two, f of x and the argument of g goes x minus x of omega t. So if the answer is so, what can be the peaks? So f and if we start the particle described by a broad wave packet f, and no matter how sharply peaked, we have a function g, the point to be left in the superposition of state, the broad range of positions. So that's how you can, if we represent these two functions as in terms of these delta functions. So, and they are represented graphically in terms of that wave vector psi. So for a particular value of psi, it's going to take value, maximum value. But that state is also combination of the other states. That's the point, superposition of the different states. So the point is that a correlation between the system and the apparatus, which is between this equation and this equation, system and the apparatus, system and the apparatus, system and the apparatus, system and the apparatus does not in itself represent measurement, because the system and the apparatus are still left in the superposition of the states. So here I'll end it by trying to just give what's the exact, how we can have an open interpretation or many-word interpretation of this thing. So what's the significant thing which differentiates one from the another, which we have talked that in one we get the observer, the measuring apparatus assigns a definite value. In the other case, the value can be different, which includes that one, and which in turn is related to how the different histories can be taken into account. But So in Copenhagen interpretation, by the time observer finishes examining the state, examining the state vector collapses to some value, you can see it. Not in that collapse that it goes into nothing. So by the time observer finishes examining the state, so here the question arises: what was then the before he was going to measure? What was he was going to observe? Was it the same, or did it remain the same? Or what actually we are measuring is that the value it took was on account of what we assigned in the process of measurement. So these are many questions associated with this question, that if it collapses to a different state. But in many world interpretation, the state vector the state vector remains superposition of what? That u of psi, this it's superposition of all these states. But apparatus includes observer. And so each term of the superposition of the state in which the observer thinks that the state has become one of the AN. So it has become, so the apparatus includes the observer, so there can be many states. Among those states, one of the states may be in which the observer thinks that state apparatus has become one of the AN. So there can be many states, but in one of them, the observer thinks that state apparatus has become one of the AN. So there can be many conundrums attached to it. How do we describe observer? Whether observer is part of the system. So can we observe a meta-observer, or an observer outside the universe or outside the system, which may be God or a metaphysical scenario? And how then can we just see it? So we in many worldviews, we are simultaneously creating worlds or many states. So that's a digression. So that's the fundamental point is that in Copenhagen interpretation, the observer chooses the state vector collapses to a definite value by the act of measurement. In the many worldview, this observer or the observer they remain the superposition of the different states. Apparatus, including the observer thinks. So here, observer thinks that state apparatus has become one of the A. That's it. So we'll stop here, and in the next class we are going to have a discussion on how we are going to what are the different problems or with these both of these interpretations, open as well as many world quantum mechanics. Thanks.